In section 4.8, we close out this section. So keep in mind, section 4.9 we talk about much later when we talk about electrochemistry. So skip 4.9. We're not covering that right now. But in section 4.8, we are looking at a couple more reaction types. We look at acid-base reactions in a little more detail, and we look at reactions where a gas is evolved. Well, first we have to know what the strong acids and strong bases are, both in terms of the strong acids being strong electrolytes, that's the same for the strong bases, but also in terms of these strong acids can pose an extra hazard. So this is another one of those things that we have to memorize, what these strong acids and strong bases are. If it's not on this list and I don't tell you otherwise, you can assume that it's a weak acid or a weak base, which means it's not as hazardous and it's a weak electrolyte. So what is an acid-base reaction? Well, we already saw previously that the net ionic equation for a acid-base reaction is H plus and OH minus, and they form water as a liquid. So we have a definition from Arrhenius of acids as things that can produce hydrogen cations when placed in water, and bases are things that can produce hydroxide ions when placed in water. So any soluble salt that will release H plus or OH minus is considered an acid. Now, in this book, they talk about hydronium cations, which are H3O plus. Hydronium cation. And their idea here is that we have a proton, if we talk about H plus, and a proton with no electrons is just a subatomic particle. So how can we refer to this as this individual atom with its own properties, when in reality it's just a proton with no electrons? That's a pretty unstable situation. So in reality they say, okay, it must bind with water, which it does, and form H3O plus, which it doesn't. So this is not something I really care for, but we have to deal with it because it's in this book. So what is this that bothers me about it? Well, one thing is in reality, there isn't just one water molecule. I don't really have H3O plus. What I really actually have is something more on the magnitude of H41O20 plus, which is just ridiculous. And if you can imagine trying to put this into an equation and balancing it, it's just unfriendly, to say the least, right? So H3O plus really isn't representing the real situation in water anyway, so why are we going to complicate our lives by using it? On top of that, it's not like all the other cations and anions that dissolve in water aren't also surrounded by water. And sodiums and chloride ions walk around all the time as basically H2O Na plus, or even more realistically, 3 or 4, maybe 5 water molecules. We're looking at maybe like H10O5 Na plus as the true situation in water. But when we're reacting things, we really don't care about the fact that it's surrounded by this network of water molecules that helps it stay dissolved until it meets a partner that it can't actually stay dissolved with. So we can treat it just as sodium ions, just like we can treat a hydrogen just as a hydrogen ion. No reason to make our lives more complicated by trying to say, oh look, it's associated with a water molecule, or 20. Okay, so what do you have to know for this? In general, you have to know that you might see in your book or in other sources H3O plus. I want you to know that that is exactly chemically equivalent, is no different than H plus aqueous, a dissolved hydrogen ion. The only function that we have for H3O plus existing is it makes our lives more difficult when we try to balance equations. All right, finally, sorry, divergent there. What is an acid-base reaction? Well, acid-base reaction is an acid, remember, things that give us H plus, reacting with a base. Arrhenius said those give us OH minus, and it forms a salt and water. Well, the water is just HOH connected together. That's the hydrogen and the hydroxide put together. The salt is everything else that brought the H plus and the OH minus to the solution. So it's as simple as that. You take the H plus and OH and make water, and you stick the other stuff together and call that a salt. Salts, by the way, in case we haven't mentioned this before, is just another name for an ionic compound. Table salt is sodium chloride, but it's a salt because it's an ionic compound. All right, so we've done a large number of these acid and base reactions already. Hydrochloric acid plus sodium hydroxide. What does this make? H and OH go together to form water. Section this off. And what's left over? Sodium is the cation, chlorine is the anion. They go together. There we go. That's it. That's an acid-base reaction. H2SO4 plus lithium hydroxide. What do they make? They make water, like all acid-bases equations do, and whatever's left over, which is lithium and sulfate. I have to balance this out. So 2 lithiums for every minus 2 sulfate, 2 of those, and we're done. But in terms of predicting what the products are going to be, the products will always be water and whatever's left over. So there's a special kind of acid-base situation that we take advantage of a lot in order trying to analyze unknown substances. And what this is a acid-base titration. Okay, so here's where we try and take advantage of the fact that this reaction between acids and bases gives us water and gives us a neutral solution that isn't acidic or basic only when I've used up all of the hydrogen ions and I have nothing but water molecules left, and therefore I can add substances to that solution that change color or do something else for me when it's a neutral solution with no hydrogen ions left, and I can find out visually when I have a neutral solution, when I've exactly used up all of whatever's in that flask. Okay, so we have some definitions here. First of all, this big piece of glassware with these really nicely defined markings on it so we can tell exact volumes. It's called a burette. Spelled a variety of ways. It's an E, etc. Depends on how French you want to make the name. But this is a burette, and there's some pieces to it which we'll talk about another time. But you put a titrant, that's something you know the concentration of, inside the burette. In this case, we've used a base. We're going to add that to an analyte, something we don't know the concentration of, but the titrant reacts with. And then we're going to titrate or perform a titration by adding the titrant to the analyte. And then something that changes color exactly when we get to the point where everything is exactly used up of the analyte by adding the titrant is called an indicator of some sort. And we'll talk more about the details of this later, but this is the basic parts. And this kind of sums it up. The one thing we didn't say is that we have a term for when the reaction is exactly at the point where what we've added in terms of the titrant has exactly used up the moles of analyte, and we call that the equivalence point. So when all of the acid is exactly used up by the added base, or vice versa if we're analytes something else. But this is the key part to a titration. It's where the moles added or the moles are the analyte. Where those two things are equal, that's the equivalence point, and this is what we're going to base our calculations off of when we look at these types of reactions. All right, so let's look at an example of that. Let's say we're going to titrate 10 milliliters of hydrochloric acid. We don't know the concentration of it, but this is our analyte because we don't know the concentration yet. That's what we have to find. Now, keep in mind, this whole thing is basically just going to be another one of those molarity stoichiometry problems that we saw a few sections ago. It just has a different name and has a little bit of different terminology. So that titration of this solution requires 12.54 milliliters of 0.1 molar sodium hydroxide. Okay, so that is what we know. So that's the titrant, the known concentration solution that we're adding to the analyte. And here's exactly how much we have to add before the indicator solution changed color. And we said this is the equivalence point. And the equivalence point we said is where moles of titrant equals moles of analyte. Okay? Excellent. So we've exactly used up, we've added exactly enough moles of one for moles of the other. So let's look at this. What's the concentration of the unknown hydrochloric acid solution? Well, the concentration is going to be in molar units, or moles of HCl for every liter of HCl solution. Well, we already have the milliliters of sample of hydrochloric acid solution. So we can turn that into liters and put that down here at the bottom, and we're already halfway done with the problem and we barely started. Now the next step's a little harder, but let's see what we have to do. 12.54 milliliters of HCl solution. We're going to calculate from here into, oh, that's not HCl solution, that's sodium hydroxide solution, my mistake. Okay, so we're going to take that sodium hydroxide solution and react it with the hydrochloric acid. So to get this right, we're going to need a balanced chemical equation. But we know how to do those. Acid and base forms water, and whatever's left over, 1-to-1 ratio. Everything here is a 1-to-1 ratio. Good. So let's calculate our way across using the molarity of the sodium hydroxide, just like we would with any stoichiometry problem that included solutions. And we have a 1-to-1 ratio between the analyte and the titrant. And that should get us moles of HCl. So 12.54, I'm going to calculate, it wouldn't turn on, there we go, 12.54 divided by times. Oh, look at what we forgot to do. We're in milliliters still. So we need one little step in between here and there, don't we? We can't cancel liters with milliliters. So 12.54 milliliters of sodium hydroxide solution times 1 liter every 1,000 milliliters. Good. Now we're in business. So 12.54 divided by 1,000 times 0.1 gives us, not surprisingly, 0.001254 moles of hydrochloric acid. So that's it. That's the only information we needed to complete this problem and find the molarity of the hydrochloric acid. So what is that molarity? I have 0.1254 molar. This molarity is 3 significant figures, so we have to truncate to 3. And the unknown analyte concentration is discovered. We're going to do a lot of these problems at some point here, but just kind of keep in mind this is no different than a molarity stoichiometry problem. For gas evolving reactions, we're not going to get too much into this. We just want to point out a couple of examples. If we have a sulfide, meaning something that has S-2, and we react it with a strong acid, what we're going to get is H2S gas. And that's just going to form by having the H pluses react with the S minuses, and then whatever else we have is left over turns into a salt. If we have carbonates or bicarbonates, so that's CO3 minus 2 or HCO3 minus, and we react that with an acid. Then what we're going to get is carbon dioxide. And the way that works is the strong acid and the carbonate form water vapor, CO2, and again, whatever's left over. So in this case, potassium and chloride. Sulfates and bisulfates, so SO3 minus 2 or HSO3 minus. Add this to an acid, and what I get is SO2, sulfur dioxide gas. The reaction will look exactly like the carbonate bicarbonate one, except instead of CO2, we have SO2. And then the final one, if we add ammonium, which is NH4 plus cations, and some sort of strong base or provider of hydroxide, we're going to get ammonia gas and water and whatever's left over. Okay, so ammonia is the gas, plus water is liquid, plus whatever's left over, potassium and chloride. That's as far as I really want you to be able to do this. So if I give you a reaction, I want you to be able to predict what the products are, but beyond that, it's no different than anything else. So let's try this. Hydrochloric acid plus lithium sulfide. All right, we see it's a sulfide, so we know we're going to get H2S gas if we mix it with an acid. So H2S plus whatever's left over, lithium and chloride. Now we just have to balance it. 2 of those, 2 of those. Good. And the gas is dihydrogen sulfide gas. All right, well, what if we have a carbonate? Let's see, hydrofluoric acid plus potassium carbonate. Okay, so we said we'll get CO2 and water and whatever we have left over. So potassium and fluorine. Okay, so the carbonate is used, hydrogen's used. There we go. So 1 carbon, 2 potassiums, maybe 2 fluorines, good. 2 hydrogens, 3 oxygens, 1, 2, 3 oxygens, good. That's balanced. So you can kind of just see how this goes. Just follows the same kind of pathway. What you get looks like these reactions, and specifically you get the various gases just by mixing whatever specific reagents together. And that's it for Chapter 4.